So, we have seen the basics governing equations for the coupled mode equations, which are used for the coupling analysis of optical waveguides. And now that with that background, we will continue our discussion for a very useful device, that is what is called the planar directional coupler. We will use this planar directional coupler analysis, but this can be extended to, with the background, with the knowledge of this analysis, we can understand the principle of other forms of the waveguides. So, that is why it is very important, and also this directional coupler is a very useful component, a host of many devices in optical communication, in sensor, in integrated optics. So, this is one very important device used in integrated optics, fiber optics, a very useful component. We will look at how this directional couplers have encroached almost every part of the communication system, and also a very useful device for sensors, optical sensors. Then many of the devices are like very important in terms of this optical amplitude modulator, power tapping, then power divider, splitter, combiner, wavelength filter, wavelength multiplexers, optical switch, optical cross connect, and there are many more. In fact, it is a large number of components are made out of this basic principle of directional coupler. And if you look at the structure of the waveguide, is basically consists of two channel optical waveguides placed close to each other, so that the field of the individual wave can in the mode, the field of the modes of individual waveguide can interact with that of the mode of the neighboring waveguide. So, let us look at this configuration. You have an optical waveguide, which is waveguide 1, and you see that the waveguide can support a single mode, that is the fundamental mode, which looks like this, and you have another waveguide, which is, for the time being, we assume that this is identical or maybe similar. It also supports a similar fundamental mode field distribution, and now these two waveguides are lying parallel to each other with a small gap between them, and the wave is traveling along the z direction. In that case, if we assume that we have excited one of the waveguides, let us suppose this waveguide, we launch field optical wave into this waveguide, then the modal field of the optical waveguide 1 will be intercepted by the waveguide 2. Let us look at this, will be intercepted by the waveguide. You can see that this modal field is now being intercepted by this waveguide 2. So, it hits the second waveguide. Therefore, this field, because any field in such a waveguide structure will be continuous, the tangential component of the fields will be continuous across the waveguide interface. So, this must be continuous, and the continuity of the fields at the boundary of the waveguide 2, some fields get excited inside the second waveguide, and these two waveguides, the total system is a bound structure. In a bound structure, the fields, wherever it is, it cannot be any arbitrary field. It cannot be any arbitrary field. The field induced in the waveguide 2 must be a modal field of the system, and that is the main point, that the field which is induced into the second waveguide because of the intersection of its evanescent tail with the second waveguide must be a modal field of the system. The modal field follows a distribution which is similar to that of the waveguide 1, and the induced field of the waveguide 2 interacts back with the waveguide 1. So, it so happens that if this field can interact with this waveguide, the field which will be induced here, that can also in turn interact with this waveguide, the first waveguide, and this process goes on as long as these two waveguides are interacting and lying parallel to each other. So, on the whole, if we look at the total structure as a whole, it happens that the fields of the two waveguides will start interacting with each other. Waveguide 2 will tap optical energy from waveguide 1, because the waves are travelling along the z direction. For the travelling of the wave along the z direction, it needs power, and therefore, it will tap, the power tap occurs from waveguide 2 to waveguide 1. No, it occurs from waveguide 1 to waveguide 2, and in turn, as the interaction goes on, then the similar process will occur between the waveguide 2 and waveguide 1. So, there is an exchange of power between the two waveguides due to overlapping of the field outside the guiding region, that is outside the core of the two waveguides. So, this is called evanescent coupling, because the entire process is due to the interaction of the waves through their evanescent tails. Now, this qualitative discussion understanding helps us investigate how the power exchange between the two waveguides takes place, and we will look at the exact formulation and the set of coupled mode equations to draw this conclusion. So, now we will begin this analysis of directional coupler. So, for individual waveguide, the fields vary as z as a equal to a0 e to the power of minus I beta 1. This is for the first waveguide, and for the second waveguide b equal to b0 e to the power of minus I beta 2. So, these are the two individual independent waveguide modes we are talking about. The amplitude of a mode z of a mode at z is dA dz. So, as long as this is an individual independent waveguide, the amplitude variation of the mode will be like this, and for the second waveguide, the amplitude variation will be like this. This thing is true as long as these two waveguides are isolated, optically isolated, and they are not interacting, as if they are well separated. The fields of waveguides do not overlap, and they are optically isolated. Now that, so this is the situation that we are discussing when these two waveguides are quite apart, but when they are close to each other, the fields will interact with each other, and this is the structure, the schematic of this directional coupler structure. You have an input port here, you have another input port here. You can use any of these two as an input, or you can use both of them. Then this two waveguides who are very close to each other at this region will interact, and there will be a redistribution of power at this point, which will give rise to the wave along this waveguide, which we will call the transmitted or the throughput waveguide, and this one which will be called the coupled waveguide. This will be called coupled waveguide if this is the input waveguide, then this is the transmitted or throughput, and this is the coupled. But if this is the input waveguide, then this will be called the coupled waveguide, and this will be called the throughput or transmitted port. So, this is by convention, because it is a directional coupler, so and bidirectional. So, both of these, any one of these or both of these can be used as the input, and this side can also be used as input. So, they are also sometimes called bidirectional coupler. When the waveguides are in the vicinity, that is when we look at the waveguides when they are closely spaced, that is they are optically interacting, the modes overlap through the evanescent tails. We have seen that. So, the waveguides are then interacting optically, and the result is that instead of del A del z is equal to minus I beta 1 a, you have one more term sitting here, because this is the interaction term, this is the variation in the z of variation in the amplitude of A is a function of the amplitude of the wave in the waveguide 2. So, this is the coupling term. Similarly, for the waveguide 2, you have the coupling term which is due to the waveguide 1. So, these are the coupled mode equations which we have derived, and we have seen how they have come from. Now, this K12 and K21 they will represent the strength of interaction. If it is large, then more will be the interaction. If it is small, then more will be the less will be the interaction. So, they are called the coupling constants K12 and K21. The coupling constant, you can see that in absence of any coupling, if they are well separated, these two quantities will become 0, K12 and K21, they will become 0 because there is no interaction. But in presence of interaction, the amplitude of mode in a waveguide depends on few other parameters involved in this configuration, particularly depends on that of the other. The amplitude of the field in one waveguide depends on itself as well as the field on the other waveguide. You can make out from here the amplitude, z dependent amplitude depends on the amplitude of this waveguide and also that of the other waveguide through the coupling constant. The coupling coefficient, this K12 or K21, is a very complicated function of few parameters. They all depend on the width of the waveguide, the refractive index profile of the two waveguides involved, their separation, which is very important. If it is well separated, then there is no interaction, coupling coefficient drastically reduces, becomes 0, and the kind of modes they are interacting. It also depends on the kind of modes, whether they are fundamental modes, whether they are first order modes, they are interacting. So, that is going to decide the coupling coefficient as well. And very importantly, it is also a parameter that depends on the wavelength of operation. And this principle that the coupling coefficient depends on the wavelength of operation is utilized in many interesting devices like wavelength division multiplexer, wavelength division couplers, and so on and so forth. For a pair of identical waveguides, let us suppose that constituting these two waveguides, they are identical. In that case, K12 and K21 will be identical, and therefore, this K12 equal to K21 we can write equal to kappa. So, one coupling coefficient that will represent the entire system. Now, we make a general understanding and a postulate that if we think of the total structure, the composite waveguide, then there will be a wave which is travelling through this waveguide structure with a phase constant beta, and this wave of this composite structure, the total structure, has to come from the waves of the individual waveguides, that is the modes of the individual waveguides, and therefore, this composite waveguide must be drawn out of the combination of the modes of the individual waveguides. The waves in the waveguide 1 and 2 are then should be expressed in terms of the wave of the composite structure. I call this wave of the composite structure as having a phase constant beta. So, the z dependent amplitude of the first waveguide should be represented by this, and where the amplitude is A0, and for the second waveguide the z dependent amplitude will have a similar distribution, that is B0 e to the power of. So, this beta is now the wave which is travelling along the total structure with a phase constant beta. So, this is the same beta. So, if I now substitute this assumption that there is a wave of the total system, and we substitute these waves back into the wave equation, the coupled mode equation, then we can write this coupled mode equations in this form. So, we get from the coupled mode equation I beta, because this is d del A del z will give you I beta, and this was already I beta 1. So, I can rewrite in this form. The equations simplify to the following matrix, because you can put it in the form of a matrix which will give you the coefficient matrix for A0 and B0, that is in terms of beta, B1, K21 and K12 in this form. Now, for the solutions for A0 and B0, this non-trivial solution, this determinant of this matrix will be put equal to 0, which will give you an equation, quadratic equation of beta square. Because we are looking for a beta, we have assumed that there is a beta, there is a total wave for the composite system which is propagating with a phase constant, with a propagation constant beta, and we are looking for this beta in terms of the amplitudes and propagation constants of the individual waveguides. So, look at this beta square, beta has come up in the form of a quadratic equation, beta square equal to beta into beta 1 plus beta 2, this, and this gives you this solution for beta S A, because it gives you two solutions for beta, one is beta S and beta A. These suffix beta S and beta A are very usual to represent that S means symmetric, A means antisymmetric. So, you have two values of beta, half of beta 1 plus beta 2 and 1/4 of the difference, that is delta beta square plus k square, where this kappa square is under root of this k kappa 1 2 into kappa 2 1. So, this composite waveguide has a set of two independent modes, because we started with the assumption that the z dependent amplitude for the first waveguide and for the second waveguide are drawn out of one wave which has a propagation constant beta, but it turns out that this total system has two modes, that is one symmetric and one antisymmetric. These two modes will have two different propagation constants as a solution of these quadratic equations, which are beta S and beta A, and are given by this equation. So, one of these two waves of the total system, the composite system, is propagating with a propagation constant beta S, and the other one is with a propagation constant beta A. So, this beta S is to represent that symmetric mode, and this one to represent the anti-symmetric mode. Therefore, we have the general solution to equation 1, that is the assumption that is Az and Bz, how it depends on the amplitude of A and B through interaction, A by itself. So, Az and Bz we can write in this form, having known the values beta S, beta 1, k 1 and k 2. So, we can represent in this equation. This S and A, as I have mentioned earlier, are to represent symmetric and antisymmetric modes of the total system of the composite waveguides. So, this beta S, that is symmetric wave, will have a field profile like this. You know, this is the even mode, and this will be antisymmetric, which we call the odd mode. So, these are the total system. You have two waveguides, and the modes of the total system, the two lowest order modes of the total system can be thought of. There is one symmetric mode and there is one antisymmetric mode. So, these are the two modes which belong to the total system, that is the, and we can assume that we can put the boundary condition that at z equal to 0, if we at z equal to 0, if we launch unit power into one of the waveguides, I just launch unit power into one of the waveguides, then these two amplitudes will be added up, because the phase difference is 0 at z equal to 0. Both of them will have z equal to 0, phase difference between them is 0. So, they will be added up, and these two will be cancelling each other. So, it is like as good as telling that there is a wave which is confined only into one waveguide. So, the superposition of these two waveguides at z equal to 0 will be equivalent to the wave at the first waveguide, that is an input in the first waveguide. The input unit power is launched into waveguide 1 and no power launched into waveguide 2. Under that condition, then we can write As plus AA equal to 1 at z equal to 0, because you have e to the power of I beta S z e to the power of minus I beta a z, both z's are 0. So, you get this one. So, this is the total unit amplitude at z equal to 0, and for the second waveguide this will be put equal to 0, because this is the amplitude in the second waveguide, this is in the first waveguide. Okay, so, this yields that A s is equal to this, because if you solve these two, if you eliminate the values and calculate the value of A s and A a by solving these two equations, you can see that A s equal to this, and this should be A a, there is a mistake, this should be A a will be equal to this. Therefore, knowing these facts, that we can now put them back into A z and B z equation which we have assumed, then we can write this amplitude, that is the power which is the square of the amplitude in the first waveguide, can be represented by this equation. And so, this is the power transfer equation, and B z square, the power in the second waveguide, which can be represented by this equation. If I substitute this A s and A a back into the equation for the power of the individual waveguides in this equation, A z and B z, in place of A a I will substitute that, in place of A s I will substitute the terms containing that beta 1, beta s, beta a and k 1. So, this quantity, if I will get this power transfer equation, and this is the most general form of power transfer for weakly interacting waveguides in the form of directional couplers, and this A z square and B z square are the powers in waveguide A and waveguide B, or waveguide 1 or waveguide 2. So, this equation is very useful and is very general when you consider two identical waveguides, then you can. So, we write this equation in this form, A z square and B z square. You can see that there is the periodic exchange of power between the two waveguides, that is the periodicity will be twice pi, this k twice pi by lambda, this quantity. So, 1 upon pi by this quantity will be the periodicity of the power transfer, which will be periodicity along the z direction between the waveguide 1 and 2. So, it is obvious from this that there is a periodic exchange of power between the two waveguides. If we now consider that the two waveguides which are forming this directional coupler, they are identical, in that case the modes of the individual waveguides will be the same, and they will be represented by the same propagation constant, that is beta 1 equal to beta 2 is equal to beta naught, let us suppose. In that case, then beta s will be equal to beta 0 plus. So, this will become kappa, and beta s will be equal to beta 0 minus kappa. If you go back and look at the equation for kappa 1 1 and kappa 2 1. So, beta s and beta a are now having this reduced form. So, then for the symmetric mode, beta s will become B 0 equal to B a. So, you can look at the governing equation for B a and B 0, and for antisymmetric mode you see that there is a minus sign. So, they are pi by phase, out of phase in the second waveguide, and that is what I have shown here. If this amplitude is plus, this will be minus for the second waveguide, whereas in this case both of them are the plus amplitude. So, beta 0 equal to minus beta a, whereas beta 0 equal to. So, this is for the symmetric mode and this is for the antisymmetric mode. This means, it is very interesting to see that this beta 0 is the part of the amplitude of the field in waveguide 2, and beta a 0, sorry, B 0, this is a 0 is the field in the waveguide 1. So, they are now identical and they are of the same phase. That is why in a symmetric mode you have this and you have this, both of them are having the same amplitude distribution as well as they are having the same phase, whereas for the antisymmetric mode your in the B0 equal to minus A0, that means in the waveguide A this amplitude is positive, but in the waveguide B this amplitude is negative because of this minus sign, but they are having the same amplitude because B0, the magnitude of B0 and A0, they are same. So, that very nicely explains this even and odd modes, that is the symmetric and antisymmetric modes, as an outcome of this couple mode equation calculation for the identical waveguides. Now, we have seen that if these two waveguides are identical, and if I substitute this beta s and beta a by beta 0 plus k and beta 0 minus k back into this equation, then we can write this expression for the Az and Bz in this form. It requires a simple algebraic calculation manipulation. So, you can show that the amplitude in A is a sinusoidal function sine of kappa z. Amplitude is in B is also a sinusoidal function, but with a phase difference of pi by 2, initial phase of pi by 2 with this. The power in waveguide 1 and waveguide 2 is then the mod square of Az and Bz, which gives you cosine square kappa z, and Bz square will give you the sine square kappa z. So, these are the two power transfer equation which comes from this Az and Bz calculation. Now, coupling length in the power transfer equation, if you look at this, or the power transfer equation for non-identical waveguides, that is the general waveguide where two waveguides are dissimilar, then this is the equation, governing equation for the power transfer. So, here if we put that z equal to pi by 2 and under root of this quantity, at this distance the length of the interaction between the two waveguides, you can see if we put the value of z back into that equation, the length corresponds to maximum power transfer, because this will give you a sine function equal to 1 and cos function will become equal to 0, and this length will be called the coupling length. So, over the coupling length, the maximum transfer of energy, that is Bz square, will be equal to this for non-identical system, but if they are identical, delta beta will be 0. So, this will be equal to 1. So, that is maximum transfer of energy will take place from A z square, and A z square at that moment will become equal to 0, and this will become equal to 1. So, thus the maximum transfer of energy depends on delta beta. If delta beta is there is a mismatch between the two waveguides, then power transfer is not maximum. It is not 100%. The field amplitude of waveguide 2 is much less than 1. This we can show with a plot, computed plot of the amplitude transfer for waveguide A. This is how it varies. There is a small change because of the interaction, and in waveguide only a small part of the wave is coupled over the interaction. So, this is the coupling length over which the maximum transfer of power takes place. This is the cross back state, when again the power goes back into the first waveguide and so on. So, this is a periodic exchange of power between the two waveguides when the two constituent waveguides are dissimilar, they are not identical. But if delta beta equal to 0, you have this is the coupling constant, coupling coefficient, and the length that defines the coupling length now comes out to be pi by beta s minus. So, this is the difference in the symmetric and antisymmetric modes that gives you the coupling length, and then the power transfer equation comes out like this: Az square equal to cosine square kappa z, and which is very well known for identical waveguide couplers, and is the foundation for many devices, for understanding many interesting coupler devices, where LC, if I put back, you get that B z square equal to 1 back into this equation. If you put LC for z, then you will get beta square equal Bz square 1, Az square equal to 0. That means the complete transfer of power has taken place to waveguide 2 from waveguide 1, where the power is now 0. So, this means entire power gets transferred from waveguide 1 to waveguide 2, and if it so happens, then beyond this there will be again transfer of power from waveguide 2 to waveguide 1, which is called the cross back state or the coupling back state, and then we can depict this power variation in the two waveguides, where you can see that there has been a complete transfer of power taken place between the two waveguides, and this is the LC, the coupling length, and you can also define the length over which the power in the two waveguides are exactly 50-50, and that is what we call a 3 dB directional coupler. We will see some interesting applications of these 3 dB couplers in the following sections. So, to have a visual flavor of how this coupling takes place, you have an input power in the waveguide 1, and it goes to waveguide 2, and then it again comes back to waveguide 1 and again goes to. So, in this way the periodic exchange of power takes place back and forth between the two waveguides. This state is called cross state, because you have entire power switched to the second waveguide. This is cross back state, where the power is restored back into the first waveguide. Okay, so, this is the super modes beating picture, very interesting to understand. I talked about this, that if you have a, so this is the total, the two modes of the composite structure, which are the odd mode and the even mode. The superposition of these two modes at z equal to 0 gives you, just add them up, because there is no phase difference between them. So, these two amplitudes will be added up to get a power in the first waveguide, which can be assumed to be the input in the first waveguide, and as it propagates down the total, the two modes, there is a, the two modes are characterized by two different propagation constants. Therefore, they will develop a phase difference as they travel down. When the phase difference is pi, that is the phase difference is pi, then you have to subtract this mode from this mode, which will now add these two, but subtract these two will make it 0. This will be added up, you get the entire field into the second waveguide. But if the phase difference is 0, you have at the input, then you have the entire power in the first waveguide. But there is a position which is in between these two states, where the phase difference is just pi by 2, then you will get half of the power in this waveguide and half of the power in this waveguide. So, this is what we call that 50% coupling state of the two waveguides. So, this is the beating of the two super modes. You have the two normal modes of the structure, the even mode and the odd mode. It is like the modes of a coupled pendulum. So, when they are in phase, you have one system to oscillate. When they are out of phase, the other system to oscillate. When they are in between, then both of them are oscillating with 50% of their power or energy. So, this is a very interesting fact, that by considering the super modes of the structure, we can explain the coupling of the modes of the composite structures. So, in this discussion, we have considered this planar directional coupler, and in terms of the coupling coefficients, we have also looked at the power transfer equation for the general waveguide when the two waveguides are non-identical. We also looked at the two waveguides when the power transfer when the two waveguides are identical, and finally, we looked at the configuration visually through the super modes beating picture. Thank you.